All right, good morning, everyone. Thank you so much for joining us for the first Princeton Robotics seminar of the semester. We're very excited to kick things off. Just a couple of logistical announcements before we get into it. So if you are an undergrad in the robotics minor, make sure that you log your attendance. And we're going to look at the time of the attendance, so make sure you do it while you're sitting here in the seminar. That's number one. Number two is if you're interested, everyone's welcome to come to the robotics lunch following the seminar. It will be in the F wing. So first come, first served on food, but we'll hope you'll come and have questions for our speaker. And with that, I'll turn things over to Ani.
All right, welcome everyone to the first robotics seminar of the academic year. So I want to thank Tom and Jaime for organizing the seminar this year. And today it's my pleasure to introduce my friend, former lab mate, and also former colleague, Brian Ichter. So Brian is a co-founder of Physical Intelligence, where they're leading the charge in scaling up robot learning and building generalist robotic policies. But long before that, Brian was a PhD student at Stanford in Marco Pavone's group in the Aeronautics and Astronautics department, which is where I spent my postdoc year before joining Princeton. And at the time, Brian was thinking about various things related to motion planning. So he was thinking about how we can accelerate motion planning using GPUs. He was also one of the first people to really think deeply about how we can use machine learning to make motion planning more effective and more efficient. But I think I really got to know Brian not in the lab, but on the soccer field. So just to kind of lay the scene here, this is an intramural competition at Stanford. A bunch of kind of different groups from different departments, mostly PhD students, some faculty, postdocs, came together to play soccer. And it was a kind of pretty casual and not super competitive, I think, league. Most people were there just to have some fun. It was a lab bonding activity. But not Brian. Brian was there to win. He was not messing around. When you first kind of talk to Brian in a professional setting, he comes across as relatively calm, collected, reserved. But yeah, I saw someone on the soccer field who's a real competitor, kind of real edge, desire to win, to improve, and also to help people around him improve. I saw him organizing teammates, dictating strategy, and putting in the hard tackle whenever necessary. And I think that was, for me, the first time I was like, wow, this is a person who's not satisfied with just an average level of performance and someone who wants to do special things and has the potential to do that, which he did. So after graduating from Stanford, Brian joined Google Brain, which then later became Google DeepMind. And there, he and a number of colleagues were the core kind of contributors and also leaders of this work that happened just a couple of years ago, but has already become seminal. So in my mind, it started with SEICAN, which demonstrated to the world the power of large language models in robotics, so thinking about high-level reasoning, some planning. And that then led to this really kind of long and influential line of work on vision language action models, starting with RT1, RT2, and its many variants, that connected the kind of pre-training capabilities of VLMs from this large-scale internet pre-training down to the fine-grained robotic control for manipulation. And this line of work has been hugely influential, kind of massively impactful in shaping the directions of the field that we now see today. About a year and a half ago, Brian and a number of colleagues left Google DeepMind to start Physical Intelligence in an effort to really scale up robot learning. And today we're going to hear about some of the lessons that they've learned, things in terms of data, architecture, models, and also some organizational things that allow them to release some of the most powerful models that exist today that are already becoming the kind of de facto standard that people benchmark against, and also models that people actually use, not just in academia, but elsewhere as well. So Brian, we're super excited to have you here today. Thanks so much for taking the time.
Thanks. Yeah, thanks for having me. Yeah, I think the trouble with releasing something to benchmark against is that everybody beats it in every single task, but hopefully we're getting better and harder to beat. Yeah, so today I'll talk about scaling robot learning. I'll talk some about things that I've learned through Pi, and then also a number of papers and releases that we've had between models and different architecture and data changes. So to start, I'll just kind of show like where we're at now and what we really care about. So in this task, Chelsea comes in and gives some sort of high-level command, like close the cabinet, but also place dishes in the sink or wipe a spill. So it's fairly abstract and nebulous. And this scene has actually never been seen before by the robot. We just collected data in a number of environments, and suddenly the robot's able to make some inferences and understanding over this is what the sink is in this scene, this is what the cabinet is in this scene. And so really what we care about are policies that generalize to a number of environments that can make sense of some new task that it's never seen before in a setting. I think the next slide I'll have some just like quick graphic of what we really care about. We care about multiple robots, so we're not just fitting to one robot. We'd really like to be some sort of, basically a brain that you can plug in, some intelligence to a new robot, to a new embodiment. And as part of that, we collect data over a whole number of different robotic embodiments, from UR5s to Francas to ARCs to mobile manipulators, and over a number of tasks. Right now, we really think about tasks in a lot of home environments, but also some industrial. Homes are really nice because there's a ton of diversity. I know the tasks. I know them very well. I know what success looks like. So it's things like laundry and making coffee and groceries and cleaning up. But really, at the end of the day, we care about very general purpose approaches that can apply to any sort of setting. And in this case, we think a lot of the solution is scaling up. So I'll start with kind of, as Ani said, something that's like hugely, I think, influenced the way that we think about the world, what we think about is possible with neural networks, and these are foundation models. So if we look at this chart, this is basically, I can't remember where I got it from, but essentially every single benchmark that someone comes out with and how it improves over time. And what you end up seeing is someone releases a benchmark, they say it's impossible, and then the next year it's nearly beaten. I think this one, like humanity's last exam, is now like pretty close to beaten, and this is maybe a 6-month-old chart, and suddenly it's gone way up. But if we looked at robotics on this, we'd probably see like a flat line on the very bottom. And so I'll try to talk to you a little bit about what we're missing there, why haven't we been able to solve it in the same ways these. They also are able to do more and more long horizon tasks. I thought this chart was really nice of essentially, given some task that takes X amount of time, our policy is able to do it. And I think, again, as we go forward, we see this trend is continued. And I think at some point, humans are like somewhere like here. And I think on a lot of the tasks, they've actually been beaten at this point. So clearly, there is this kind of up and to the right trend, and we want to figure out how to do it. They also IMO gold. So I mean, for sure, I would never be able to accomplish this. So they've beaten me in a lot of ways. And then they can generate images, videos. Before I had a bunch of for this type of slide, I would have a bunch of models, one doing audio, one doing video, one doing images, language. And now we have a single model that can generate, kind of incredibly complex images like this. It even looks like there's a lot of physics there. There's sort of imagined physics, but if you look at the legs move or the dynamics of it, it looks very feasible. So it feels like there's something there for robotics. And now within the area of research, I started to actually put papers and citations on these, and I decided it got a little overwhelming and it was going to fill the entire page. But there's a ton of ways in which we can use them, some for planning and reasoning, some for directly writing code that we can then use our existing algorithms and reason over to specify rewards in a really flexible way, to be able to use it as part of pipelines through object recognition. We can also generate a lot of data, maybe novel scenes, novel views through these models, all the way down to low-level controls. A lot of this talk will be around VLAs, but there's also zero-shot control. And then there's a ton of other ways to do it. So I think it's a very ripe field, and clearly I think people have recognized that there's all this information that we can inherit, all this pre-existing knowledge, and we should really figure out how to use it best for robotics. So the real question is what's missing? Why, given that we have a model that I cut off some of this, but I asked it how to make a ham and cheese sandwich, and it actually gives me an extremely reasonable breakdown of the tasks. I think 3 years ago, when I was first working on Saycan, I would have tried this and gotten reasonable tasks, but not nearly as well spread, as well kind of broken down, as actionable as this. We can also do segmentation to pretty much anything over video. I think these techniques work super well. And so I'm going to focus on kind of what I think is still not there. I think we can use some of these things algorithmically, but there's still a lot of research in how do we actually transfer this knowledge? How do we directly use it? And how do we use it in a really high bandwidth way? Robotics is also just very difficult. So, I mean, it's extremely dexterous. You need a closed-loop environment. The real world is complicated, and you need to design over like a whole system. So we need to have very fast inference. We can't just like sit there and reason. The world changes around us as we do this inference. I think a dexterous task that I think a lot about is like making tea, which I have here. But to start, I took a tea bag and I ripped it open. I had to apply the right amount of force to rip it open. And there's a tea bag inside of the broader case. And you had to reason about where that tea bag was within it. Did I rip the like tag off or the string? And basically, like, these things get really, really complicated as you go deeper and deeper into it. And I mean, I think people talk a lot about Moravec's paradox. But really, I think at the end of the day, what we care about here is we're missing scale. If I look at, these other tasks it's hard to compare. Is dexterous manipulation much harder than a language task? I really don't know. But what I do know is that OXE was this big. Our data right now, it's a little bit bigger than this. Like, we've increased it a fair amount, but it's still way smaller than GPT-2, which is way smaller than Llama 3, which is way smaller than all of the most recent ones. So it just feels like there's this massive thing that's missing, and a lot of the questions maybe get answered as we scale up robotics and really try to figure out how do we get this web scale diversity of data, size of data, and quality of data. All right, so I'm going to talk about 4 sections. First, just architectures that we can learn from, that we can learn these sort of like dexterous, fast inference, and generalization. Then I'll talk about what data goes into this, how we can scale them up, and what sources really matter. Also talk quickly about, and kind of an ad for our open source models that we would love it if people use, give us feedback, build off of. Ideally, I mean, we really feel fundamentally that robotics is not solved. And so the more that we can kind of, as a community, build on these things, and the scale that we're trying to build is for the better, and kind of proliferate these ideas. And then I'll go through just a number of kind of successes and failures. This is where I'll talk a few like organizational things, like somewhat minor, but that really have mattered when building Pi. And so to start, I'll talk about architectures and essentially how we ended up in our current architecture, which is shown on the right here. And then also just a number of steps along the way. So if we start with the original VLA, so the idea was that you take a VLM. These VLMs are trained to output some discrete tokens. What if we just take actions and we tokenize them? So we just say some continuous single time step and just bucket it and then write it out in text. So this is like becomes a number of integers. And this actually like worked pretty well to essentially do pick and place. So if I said water bottle, it was able to somehow make this connection through text, through internet scale training, that this is a water bottle and that these are the actions I can do to pick it up. And we could do pick, and we could open drawers, and we could do place, and that was sort of like the end of the task that we could do. And it turns out a lot of robotics tasks are pick and place, so that's great, but we realized there's this big bottleneck where we can't really do high-frequency dexterous manipulation. So a lot of the first things that we worked on at Pi is sort of how do we enable this to do dexterous manipulation? And the first thing we looked at was essentially attaching flow matching. So flow matching works really well for continuous series. And it turns out you can learn very complicated tasks. You can learn to fold a t-shirt, to bus a table. You can ingest fairly wide data, but it also trains really slowly. So essentially this took, I think, about a month to train on some maybe like 16 H100 nodes, which just felt like way too long for the size of data that we had and for the amount that we want to scale this data. At the time, it was maybe 10,000 hours. And so it just trains really slowly. So we kind of took a step back and said, well, OK, how can we increase this training speed? We tried some things like contrastive losses, and those sped things up. But it turned out that autoregressive training in general is just much faster. So we looked at how can we kind of cast this problem from of action discretization into something that we can actually learn in a tokenized way. So the way that people are able to do these more dexterous manipulation tasks, so if we look at the original VLA, we just output these buckets. But let's say we instead do an action chunk. Action chunks seem to work really well for kind of high frequency control. So essentially, instead of outputting just the next action to take, output the next 50 actions to take. So maybe I think like around a second is where people have kind of settled as the sweet spot. But just some forward amount of actions, and then take those, and every time you reach the end of it or halfway through the end of it, you recompute and do it again. But if you look at this, these are extremely repetitive. So like, how many times has it said 17? How many times has it said 18? And then this is something that's extremely difficult to learn within language models, within autoregressive models. In general, language model companies spend a lot of time making sure that their data is not overly repetitive, doesn't have the same pattern over and over, because it just falls into a really poor loss basin. So we needed to figure out how to kind of break out of this repetitive notion. And so we looked at essentially action compression. And the maybe one of the most famous kind of compression algorithms for a more continuous signal is for image compression is JPEG compression, which is a discrete cosine transform, where the idea is you have the whole basis functions of certain cosine waves, and you can project down to these, and then just at the end sum them up and get rid of some of the last coefficients. And so with not that much, with basically 8 basis functions, you can recreate like this little area on his shoulder. And this is, I think, let's say 10% of the coefficients are kept here, so we've reduced a lot. I could even go down to 1%, and it would still look vaguely the same. And it turns out for actions, this actually can be a very good representation. So this work fast, which was frequency space action sequence tokenization, was really about how do we represent actions in a way that VLAs can learn from them. So we take these 2 trajectories, and these are just like 2 dimensions of the same trajectory. And the first thing we do is project them down to their frequency components and then have some weights over each type of frequency. You then discretize these, and so this becomes like quantized, and this is the first dimension, the second dimension, each one subsequent from there. These are essentially like bucketed and then represented in this matrix. And then you flatten it across, and then use byte pair encoding to essentially compress it down even further. And so we can compress the actions. I think it's maybe like 10%, but the other thing that we're doing is breaking this kind of repetitiveness of it. And it's actually something that autoregressive models can learn fairly well. And to take a look at what this looks like compared to like the naive binning from the original RT2 paper is so this is some trajectory over time. The actual trajectory is these white dots that are moving through. And then the colors are as I increase the frequency that we're trying to represent. So at a frequency of like 25 hertz, it actually doesn't do too poorly for this like one-dimensional signal. But as I go further and further and all the way to like very high frequency control, it just gets extremely repetitive. And again, this is because the bucketing is such that it's just repeating the same numbers over and over, and autoregressive models don't learn this very well. Now, if I do DCT tokenization, it actually, no matter what the frequency is, it learns this very well. So something we're able to actually do this kind of like high frequency action chunked control. And if we look at the error over time, we see basically DCT is very agnostic to what the actual frequency of the data is, whereas naive tokenization breaks down at maybe, in this case, 200 hertz. But if I think in practice, we're doing 50 hertz control, and it's really not able to learn this very well. You see that the policies essentially don't work at anything complicated. Now, when I learned this, so this was the original VLA architecture, or this is actually Pi0's architecture here. And again, it took 1.2 million steps to learn. So fast learns much more fast. And the problem, though, is as much as the name says fast, inference is super slow. It's like half a second to do a single chunk. And also, these chunks are over a second, and you're only executing the first half of the chunk. So you're spending the same amount of time in inference as you are in the actual training, or as you are in the actual rolling out of the policy. So I think the big thing that we saw is clearly there's something in this learning signal. VLAs are also trained autoregressively, and so this all works to train really quickly, but this is a big problem. So what if we just add back in the action expert? So now we're training with both learning signals, and you have some like joint training trade-off between the two. And it turns out you actually can recover most of the training speed. It's a little bit slower to train, but not in like a hugely worse way. But the performance tends to level out at 100,000 steps in this case. And I actually, when I first ran this was a very surprising data point to me that it got worse. And I ran this like 4 times, and each time it was correct. That model had actually gotten worse as we trained longer. We train another one, similar thing. So it's either overfitting or at best plateauing at some point. And essentially, we're just like not getting this like far end performance out of this. So we had to figure out how can we actually essentially protect this model from the gradients coming back from the action expert. These action experts is in some way corrupting the gradients of it. Yeah. Yeah, so it's the flow matching expert. I think it's a 10-to-1 ratio. So it's like 10% on the flow matching expert and 90% on the loss of the discrete tokens. So instead what we did is just put a stop gradient here. So don't let the flow matching experts' gradients essentially pollute the VLM. And this, it turns out, works very well. We kind of get the best of these both worlds, where we're training as fast, and we're getting to the same performance. We're not plateauing, and also inference is about 50 milliseconds. So this really, I think, when you take a step back and look at it and see that like the flow matching gradients don't work well with a cross-entry loss of the VLM, it makes a lot of sense. It turns out, though, at fine-tuning, you kind of want to unfreeze both and just let the full network capacity be applied to it. But I'll talk about sort of first how, from a speed perspective and a performance perspective, it's really good, and what this looks like in practice, and then I'll also talk about like specific quantitative results with these. So again, fast, it turns out had fairly slow inference, but the performance was very good. The training speed was very good. Whereas this knowledge installation is kind of the best of both of these. And I think here was actually fast inference, and here is knowledge installation inference. So we're able to fold, like, I think it's 4 shirts by the time that this one's able to fold a single one. We're able to basically bust the table in, I think, a 10th the amount of time. There's also a little bit where fast can be fairly slow at the start. I think in like multimodality, it doesn't seem to commit as well as a action expert-based policy. And if we look at the absolute performance, we indeed see that performance is a lot better. I think that this is on this task where we have a couple items that we put in a drawer. This is actually an unseen environment. So we've never collected data here. There's like a camera mounted to the ceiling, and we just wanted to make sure that we never had any data there. We wanted to make sure that it was held out and something that we could really like control. And here we see that the absolute performance is much higher. Joint training is still pretty good. Pi0 and Pi0 fast are a good bit worse. And then if you kind of just freeze the VLM, which a lot of people have also tried, performance dropped a fair amount. I mean, this is like an efficient way to do it, but it's just not expressive enough. And when you have enough data, this doesn't learn very well, especially for a held out scene. I think in a scene in which you've seen before in the data, in a distribution scene, this might work a little bit better. But as you go out of distribution, the performance drops off. In terms of speed to actually execute the policy, again, knowledge installation is much faster. Joint training surprisingly slows down a fair amount, but so do all the other comparisons. Again, frozen backbone does very poorly. I think just like anything out of distribution, doesn't seem to work very well. Fast and Pi0, and this is removing the inference time. So I think here, like, fast would really be up here because it's just so much slower at the actual inference. And then the other thing that I really care about, and I'll talk a little bit later why, is language following. So, I mean, first, VLMs are starting with this ability to follow language. They understand language, and it's something that we'd like to really inherit from them, just so that they're more controllable for us, but also for algorithmic reasons that I'll talk about later. And indeed, with joint training and also with knowledge installation, we see that the language following is much, much better. Essentially, we are recovering and keeping a lot of the initial VLM knowledge. This is where this like knowledge installation comes from. We're essentially protecting this initial knowledge, these pathways, from the action expert that's ultimately performing the actions. And it matters in distribution, out of distribution. These are not actually directly comparable because the tasks are slightly different. But what's important to see is that both these ones with joint training or with knowledge installation just preserve language following at a much higher degree in distribution and out of distribution. So the second part of my talk is going to be about the data that goes into this. And on that last slide, I had a little bit of web data, and I'll go into a little more about which ways in which web data helps the performance in this one. This is really about the Pi 0.5 paper and then also our high robot paper. So looking back, I guess, to 2023, we had the open cross-embodiment data set. This was a whole number of labs. I think probably many people in the room maybe are on this paper and contributed data in some way to it. And from Google, I think we contributed like 400 hours that we'd collected over a year or a year and a half. We had another task that was 1,000 hours over a year. So like 4,000 hours of data. So about 6 months into Pi, we had about 10,000 hours of data. So I think just like this focus on scale. Also, there was a lot more dexterous and varied tasks. So I mean, the box building task is a task that I really like. It's like takes a minute to fold this box. It's really long horizon. You're watching it go, and it feels like magic when it all comes together. But we also collected in a lot of environments, and just over, I think there's hundreds of tasks. And then at 12 months, it was much more than that. We added in web data. We kept in the OXE data. We're now maybe, I don't have the next one to now, but it's like somewhere over 1,000 tasks have been collected. I don't know off the top of my head the amount of data, but it's basically continued to scale a lot more, and we've gotten to a lot more mobile manipulation data sets, including a wide variety of collection over different scenes, collected in about 100 Airbnbs throughout San Francisco to be able to get like diversity over the real world in the way that the real world is set up. And so one of the first things we cared about is just as I collect over environments. So again, each one of these is actually a different Airbnb that we rented, went in and collected a number of different tasks in, bedroom tasks and kitchen tasks. How much does this actually help in some held out environment? And so we collected, this is essentially in distribution. In our office, we made a makeshift bedroom, collected a ton of data there, and looked at the performance. And this is with a pre-trained model, and yeah, we get to like 83% performance. It turns out 100 different environments essentially match this performance. So it's never actually seen this scene. You start with this pre-trained model, and you train it over each one of these Airbnbs, and we're able to recover the full performance. So I think in some ways this is a really nice sign. It wasn't clear if this was going to be 1,000 environments, 10,000 environments. It's also not clear as I go to 10,000 how much better do I get. Presumably I can actually start to exceed this in distribution performance, though we had a lot of data in this one scene to make sure that this was like, basically I think the amount of data here is the same as the amount of data here, so we collected, massively over-collected in our one scene. The other thing that you start to really see is how much pre-training matters. So this is pre-training, and I'll show some examples of what the other data looks like, but across a variety of data. And if you don't pre-train, even in distribution, we get to like 40% performance. But the out of distribution, you essentially get nothing. So even though this was a fair amount of data in a bunch of scenes, if you didn't do this whole pre-training process across varieties of data, you're not going to get this benefit. You're not going to generalize to a new scene. And also, I mean, even if you don't generalize, this is quite poor performance. The other thing that we look at is, again, language following and how this changes as number of locations increase. And what you see, I guess, to start is that in distribution, which are environment or objects that you've seen in a bunch of scenes, though maybe not in this specific scene, first in distribution performance goes up much faster. But really, by the end, these two lines meet each other. And then I think I have an overlay of these two. So the bottom ones are always the, did it actually succeed in picking up the object? And the top one is, did it go towards the correct object and attempt to pick it up? And we see that these also lag behind a little bit, that you eventually start to like recover the same, near the same performance, but it takes a little longer to learn to be actually manipulate these objects in new scenes than it takes to be able to recognize what they are. So I talked about how pre-training is super important, and really what pre-training is seeing a massive diversity of data. So it's multi-environment mobile data, it's web data, so this is like bounding box tasks, web VQA, some semantic segmentation, just like a lot of variation over things that we can basically scrape from the internet or existing data sets. It's also cross-embodiment data collected in a lab setting. So we have, I think, 20 different robots and like 5 different types of robots. Some are single arm, some are bi-arm. None of these, in this case, were mobile manipulators. A lot were ones that matched these arms, but in static stations. And then finally, we had these multi-embodiment or multi-environment collection, where you can see here we kind of just clipped a robot to different parts of the world. So you would just carry it around, take a vise, and then attach it to a part of the kitchen or somewhere in the bedroom, and then do some tasks. And it's just single arm versus all of our final tasks that we're actually evaluating on are by manual manipulation. So at absolute performance, first, we see that web data actually doesn't have this so this is, I think this is averaged across a number of different tasks. It's like making a bed, putting items in a sink. I have some videos of these later. But at absolute performance, we see that web data makes a little bit of a difference, but it's not really a huge difference. But what is a really big difference are these cross-embody data sets and multi-environment data sets. So having seen a variety of scenes helps, even though these weren't mode manipulation data sets, it makes a big difference for absolute performance. And then cross-embodiment in particular made a big difference. And then these together, the performance drops to kind of 40%, which is essentially, it's not making much progress at all. We also see in distribution language following, again, because it's in distribution, we maybe don't expect that much out of web data. And indeed, we see this, that web data doesn't really change at all the absolute performance of following a language command. What does start to change are these cross-embodiment and multi-environment data sets. And again, together, this matters even more. So really, I think what we see is each one of these steps kind of adds upon itself. You really want to get as varied data as possible. And then once we go out of distribution, web data starts to have at least some impact. It turns out, I have a slide later, it turns out that high-level policies is where it has a little bit more of an impact. But it still has some out of distribution language following impact. But really these ones, the multi-environment, where we've just collected over a lot of scenes, you've been able to make these correlations over what an object is in various scenes makes a huge difference. I think in this case, chance is 20%. So these are not that much higher above chance. It's a task where we're picking up a specific object that's asked for and then putting it into a drawer. And so you really do need this diversity of data. And then, so this is once we then take our policies and then add in a high-level policy on top of it. And what we see first is this is an ungrounded policy, so GPT-4, a human high level, which actually we exceed, and I'll talk a little bit about why we potentially outperform a human high level, which really you would think is kind of an oracle in this setting. But some things that I think are particularly interesting. First, web data was really important here. Essentially, the worst performing of our tasks is if you just remove web data. We also collected data where we were taking a high-level policy, or we were taking a person and then they were commanding the low-level policy. And so this is, I think we call this verbal instructions. We're essentially closing the loop between a low-level policy is going to make certain mistakes. Here's how you provide corrections for it. Here's you kind of need to robustify it to the mistakes of the low-level policy. And again, that has a pretty big impact on performance. And then not having a high-level policy also has a fairly large impact on performance. One thing that was, I think, a very surprising result to me and made me feel oh, we are getting something out of this pre-trained mixture across these series of data sets, is that this implicit high level, the only difference, so we have no high-level policy in this one, but what we've done is we've also trained the policy to be a high-level policy. It's not rolling out in that way at rollout time, at inference time. It's just directly producing actions. But it had a pretty sizable impact on long horizon performance. So because just we co-trained on it, this transferred fairly well to the tasks. And it was a bit surprising because we were iterating in this regime. We were seeing a high-level policy makes a huge difference. It makes a 15, 20% difference. And we went to do our final model and test it for the paper, and the result dropped this much. And it was as someone who worked on the high level, it was oh, wow, this doesn't really matter. The high level is not helping at all. It was quite disappointing. And then we thought, well, what has changed? We've been iterating on this, and they really just don't work without the high-level policy. And we realized just by co-training with this, it had a fairly sizable impact and closes the gap a lot. So I think when you get enough diverse data, you start to just see this task sharing across things. I mean, this has been observed in language models and vision language models a lot, but it really starts with a robust representation that you're learning from, and through that you can make these kind of transfers. Oh yeah, and then why we did better than the human high level. I think I've been asked this a lot. And my main takeaway is that a human high level is trying to command the policy to do certain tasks. And if I said, pick up the water bottle, and all I cared about was cleaning up this table, I said, pick up the water bottle, and the robot doesn't listen, and it goes and picks up this cup. A high level policy, because every time it's got to pick up the cup, it said pick up the cup, will switch and basically help the low level policy just complete that task. A human will continue fighting this and try to get it to do the thing that it really wanted. And this actually in our tasks, hurts overall performance. It's led me to see this kind of like dichotomy between sort of orchestrating, which is what we would traditionally think of the high-level policies job as, and just removing multimodality. And it turns out a lot of the performance difference is because it's just removing multimodality. It's making the model commit to something. And so even if it makes a mistake, it then says, that's fine, I'll switch to this. It commits to it. And so if you have a human, for example, say, try to just like narrate what's happening, you can get this a little bit up. It's not really like the traditional role we see for high level, but I think there's something kind of like nuanced happening here. And high levels are not necessarily like playing the role that we fully expect in multimodal tasks. So this is a result from Pi0 that I thought was particularly interesting. And it's essentially, well, first, if you don't have a VLM, language following is shit. It can't follow language at all. And it's maybe not surprising, but it was a little surprising what the difference was to me. It like made a huge leap. But the other thing is that if you don't follow language, you don't get benefit from high level. This is somewhat orthogonal to what I was just saying, but it's about being able to listen to it and collapse the multimodality around that. And so what we looked at is if you have a human high level, and these results are a little bit older than the previous ones where like the human's doing as well as the high level before we like increase the performance overall of it, you actually see that you get almost no gain for this like model that isn't listening to the language command. So by having models that are trained from VLMs that listen to language, it actually opens up this whole area of high-level model research that previously just doesn't really help nearly as much as you would hope. So this means that we can also transfer concepts like reasoning. And so we have this work called HiRobot, where the idea is really, can we have the model think longer, think through something, use results from, say, chain of thought, where you're breaking down the task to improve overall performance. And it looks something like this. I say, get me a snack or something sweet, and it makes these connections across the task and is able to do fairly long horizon tasks. And what's most kind of important here is that we can actually generate a lot of synthetic data of this. Because it's just a high-level task where it's essentially VQA, you don't need the full rollout. You can kind of take a single image, and as long as you give a plausible high-level command, you can generate just a ton of diversity through either human annotation or generally like synthetic data generation. So this is, we collect data, we then label that what you were doing at this time was picking up a Kit Kat bar, and then we also label, well, what if I had asked, get me something sweet, and you know it's holding the Kit Kat bar because we've labeled this or because the VLM understands this, and we're able to essentially generate what I'll show on the next slide, a bunch of different ways in which you can interact with the model, that you can improve overall performance, and that you can sort of create new tasks out of nowhere. So the way it works is the high-level model interprets some commands, say like, get me something sweet. It breaks it down into low-level tasks that the robot's actually capable of accomplishing. It can also respond to you and ask for clarifications. And then the low-level condition on this produces actions. And the types of tasks that you can just create, you can come up with unseen tasks like, we've always cleaned up the entire table, but this time only clean up the trash. And you can also have kind of interruptions and say, given some auto labels, if I say, no, don't do that, maybe it should like open the gripper, put the object back down. We can tell it to avoid certain objects. And then we can also give these like extremely open-ended prompts or like longer horizon tasks. And when you do this, we see performance improve across a variety of tasks. We see that the policy through the high level pays more attention to what you're saying because the high level is able to make these kind of connections. And I will quickly just go through this. But the two things that really were new here, one is just how we're using the hierarchy. And clearly, because we're listening to language, because we've added all this data, this hierarchy helps a fair amount. And then the synthetic data makes a massive difference. Essentially, without it, you can't do these new tasks. You're making some connections through the VLM, but it's not able to do kind of like more complicated reasoning, like put an object down, avoid an object. It's going to fall much more towards the distribution, but because the high level is able to ingest this synthetic data, we can use this as a data source. We can do new tasks that it hasn't seen before, so like leave the dishes, essentially like every time that we collect data, we just did everything. So you take a normal policy and you just say clean this up, and it's not going to be able to understand this. It just is going to go and clean everything. We also had distractor objects like phones in there, so the low level knows to avoid these kind of things. But overall, this allows it to do some new tasks that you haven't seen before. You can also, the times that it does make a mistake, you can say, no, don't do this. And it can output something that actually commands the low level to not do it. And I think like this ability to kind of, without collecting data, interject or inject new scenes or new reasonings is really important and difficult. We can also do, from the same scene, a whole variety of long horizon tasks. So these are like different types of sandwiches, and you describe them in a different way. Like this is a vegan sandwich, vegetarian, and then I think a ham and cheese. And the policy is able to basically break this down into the series of steps, even though when we collected the data in the first place, all we said was make a sandwich. We then created all these other scenes just out of this like automatic data relabeling pipeline. The one thing that, and I'll like talk about it later, but a lot of the sandwiches look kind of gross afterwards, and I feel like these are like areas that we need to work on as roboticists. How do we specify these like much more complicated goals, which is that they can't look this gross. Okay, so a brief aside into OpenPy. So we've open sourced a series of models. And again, the idea is we feel like as a field, robotics is very far from solved. And we need to figure out ways as a community to kind of improve this, make breakthroughs, ideally be able to ride on some of the scale that we're working on. And I think we're still way under the scale that we'll eventually be at, where hopefully things start to work well. But just a quick ad to try to use all these models. We actually, it's fairly easy to run on some new robot, I think. So we released a model on Tuesday, and like hours later, people had it running on their Francas. I feel like I've seen some droid setups. So like the droid setup is supported, and we have a model specifically for that. We also have the pre-trained model. And I think this video was particularly interesting to me, if it's gonna load. So essentially, all they said was clean the table. And it's not, it's slow at times, but it figures out that this is the basket, and it's not like, we actually collect very little data on Francas, like internally. There's the droid data set, but ourselves as Pi, we don't do that much with Franca. So it's not really even that. It's like some sort of like, this cross embodiment is actually helping a lot to be able to understand this new task. And it takes 10 minutes, and I don't know how long it would take me to clean up the table, but it's not 10 minutes. But eventually it actually like gets there and cleans everything up, except these like small little things, which I think he has a follow-up video where it gets some of those. But yeah, I don't know, give it a try. It like surprisingly works somewhat out of the box. And then this one, somebody also fine-tuned it. I think they said 30 minutes of fine-tuning, and it started to work. And after 2 hours, it improved more. There were about 50 demonstrations in this, and it's like putting a ball in a cup with a robot that we for sure have never collected data on. So use it for your projects. Let us know how it works. Let us know any issues. And cool. So this last bit, I'm just going to go through a number of like things that have worked, things that haven't worked. I'll try to include failures when I could find one quickly and could add it to the slide. So this was Pi 0.5, and I think it's first just like it's never seen this environment. It's in this new scene, and all Laura says is like clean up the bedroom. It's able to understand what's trash, where the trash can is, how to make the bed. I think like it's a bit slow is maybe one thing. Like we're playing this, like we'll acknowledge at 10x speed. So clearly, even though this I think the task is really complicated and really impressive to me, and surprising that this works so well, we still have a lot of room to grow in overall speed. I think this real-time action chunking work led by Kevin Black was very surprising to me that some of these tasks work. I think this one's particularly cool. We're lighting a match and then lighting a candle. And lighting a match is particularly interesting because there's all these works about tactile sensing, where if you give a person a nerve block and they go to try to light a match, they like struggle. There's some like YouTube video of somebody just like, they can't even pick up the match. They then try to strike the match. They get nowhere. We have no tactile sensing here. The policy doesn't get tactile. The policy has a wrist camera that is giving you a very close view of what's happening, and potentially that's where tactile comes from. But we're able to learn this like very like classical, you can't do this, people can't do this task. And it was like 300 demonstrations. I think this was like one of our lead operators just collected it whenever he had free time over the course of 2 weeks. We went and tried it, and it works. I can't remember the overall success rate, but most of the failures is because it doesn't wait long enough for the match, or doesn't wait long enough to light the candle here, which our policies don't have history right now. I think this is also a very open area of research. How do we get policies to learn from history? They take a single image. I don't think I could do this task with a single image and then just like open loop play a half second of actions. So the things that we've been able to learn with fairly simple recipes are really impressive to me. I think there's like a lot of open room to continue improving. We're able to do fairly complex gestures tasks. We started with this because we knew it was long horizon. It's really hard to simulate a t-shirt fold. There's a ton of variation over it. So on the right, we have like a pretty good, pretty fast t-shirt fold, like 20 seconds. These are 2 failures, actually from the same run. It took like 2 minutes, and it got almost there, but it left it a little bit crumpled, and we didn't have much data, I guess, of having these like corrections once it's in this state. I cut it in half because it was a little bit long, but it essentially from there gets it all messed up and goes to this state. But we gave it a rollout of 2 minutes, and you'll see at the very end, after much kind of cajoling, it's going to be able to get it flat and probably back into a state where it's going to be able to succeed. So I think as much as these failures, so here I think it's going to like time out because we basically had a 2-minute timeout on it. But I think it was going to succeed at this one. And so you collect enough data and you actually start to get like recoveries out of these. This is a particularly interesting recovery where it goes to pick up the laundry and it picks up two shirts. And it's not like we collected data where you had 2 shirts statically attached, but I guess this happened a couple times and the person puts it back and it goes on and folds the laundry, straightens it out, and does it just fine. I think these are some of the things that like, when you get to scale, when you do very open-ended data collection, I think another thing that's changed from how we might have done it at Google is before a task was picked. So I picked this up and I went here. Now if I miss this, I just sat here. And that was like always the terminal state. So when you do these much more open-ended data collections, like the style tends to improve performance and robustness a ton. Some of it is just about getting to scale, but some of it is about how you go about collecting the data, how you design the task. Trying to make them much more real world and useful tends to help. Box voting was one that I think took operators like a month to figure out even how to do themselves, and now the policies are extremely proficient at it. The failures that we really see, so on the right is going to be a success, and on the left will be what we mark as a failure. It's interesting because you really have to do this sort of long horizon reasoning about where to hold it, what to pin down in order, and then when to release different parts of the box in order to have it fully construct. I actually like sometimes will go and try to do it myself and get like lost partway through. So some of this is that I'm bad at these things, and some of it is that like it's pretty impressive that the policy can do them. As we like skip forward, one thing you'll see is this box gets pretty mangled. So even though the box is like built, anybody who like really wanted to use the box in the real world would say like this box just got completely messed up by the robot. And so being able to also represent these kind of things, this is where I feel like scale is the only way to do it, like scale and labeling these kind of things, because it just, the representation of, and I guess this GIF is probably going to continue, but like this part of the box is bowed out. When this goes in, it's not going to go in very smoothly. The robot will make a correction on it, but it's basically like not an acceptable box, but like representing this is extremely difficult. That like this part of the box wasn't good. Some things that have worked really well are multi-embodiment. So this is a partner's robot. They send us some data. We fine-tune a policy and send it back to them. No one from Pi has ever like touched this robot or been there in person. And these kind of things are like working more and more. And I think as we get to enough scale, and now we have open source models that hopefully people can do this themselves. But I think it's pretty cool how much they've improved in the other tasks that we can do. So some like organizational things, and I'll keep these kind of brief, but things that we've thought a lot about. How do you get visibility over data? Actually, each one of these is a single data point that someone's collected. I can go in and click like that thing and see the point of data, see what happened. Was it a success? Was it a failure? The colors are based on tasks. I think especially when you're at a company with these scales, having visibility over everything, like this was a huge win for us and took us way longer to do than it should have. We also have visibility over like, here's everything that's going into the model. And this like gives you a lot of sanity, like always log all these things. Just knowing that it did get the command that you wanted makes a big difference. This also has like, I think this one actually fails. It's like not going to be able to get to this pillow. This is a later policy that works fairly well. It's cool to see some of the nuance of like how do you actually correct the state of the duvet? How do you like find that pillow and pick it up off the ground? What's a terminal state for that? I think these are like very impressive, but a lot of times we end up with failures like this. Other things that we didn't do that well at the start, we didn't like control things that like probably should be controlled. So like this was a camera that I placed. This is like really hard to reproduce where that was. I spent a lot of time with evals that suddenly broke and you couldn't figure out why. And now I think we're pretty robust over camera placements, but doing it unintentionally was not super helpful. This is a data demonstration. So again, I think it's a camera that looks like this. And you can actually barely perceive the motion of it. But this is over 4 hours, the same camera. So it's like moved a ton. The other thing is like at eval time, the robot is potentially going to be more jerky than during data collection, and it will move a lot more. So try to like find out these things that aren't working or that aren't controlled and try to control them. Will give you a lot of sanity. It makes like reproduction much easier, evaluation easier. Other things that we've done, we ban OpenCV because BGR to RGB is like crazy hard to figure out which way your data is. And when you have cameras of different ones, I spent like a week trying to like get this out of the code, figure out which way it was. It's just like not worth it, remove it from the start. Putting robots down like this was maybe not our best idea, and they also moved over time. So lastly, I want to talk just about a few open areas. I mean, I've hinted at a lot of these throughout, but I think speed is still a big issue. This is just another replay of the same video, but showing things at 10x is not necessarily where we want to be. Having sandwiches that look like this, like in a lot of ways, this is like a task success. But if someone gave me that, I would not be super pumped. This one is like, I think it's like it does the full fold. It grabs a piece of laundry, it folds it really well, it stacks it on top, and then it makes a mistake where it grabs it and puts it over there, and then suddenly everything is kind of like out of distribution. So figuring out how to be very robust to these types of failures, I think, is really important. Like even up to this point, I mean, it's done 98% of the task, and then it's gonna make one mistake, which is gonna cause another mistake, and it's just gonna like, now the last shirt's gonna go. It's like maddening. All right, I think figuring out how to do better data collection is really important. Like there's clearly things that I can't do with the robot that I can do with my hands. There's this like big gap. Maybe some of this is like human data, Yumi data, but I think this is like a very open area of research that also doesn't require massive scale to figure out. I think just seeing that I can collect a task, that I can replay that task on a robot, that I can actually accomplish it is just like a very important area. At the end of the day, all our models at the base start with just this data. So the quality of it, the diversity of it, being able to actually accomplish a task is really like the most important part of the recipe. I also work a lot on evaluations. I mean, I think like Russ had a whole talk about this, and that's probably the place to go to see how bad and hard evaluations are, though I can also complain about them for a while. But I think ways to offline get signal, whether it's offline losses, I think this is like an area that has sped up language model people like crazy. Being able to say, if I add this data set, it's going to help this other data set, it's going to help this absolute performance at the end of the day, and that it's like robust and reproducible is really, really important. And I think something as like roboticists slows us down a fair amount. I think action representations and how do we get actions out of web data. You know, I started with that like VO video where it's generating these like really complicated dynamics, and I think it's still not getting like the subtleties of the world of like the amount of friction to take the top off of one of these markers. But I do think there's a lot more that we can do there that we can inherit from it. It feels that we're still like massively underutilizing this. And then long horizon multimodal tasks, I think, are still really hard. Making long horizon decisions, having memory, being consistent throughout the task, I think is like very much unsolved. Whether this is potentially through planning, through language models, I don't know, but there's a huge area here. So other success, I think our team, and I'm like very proud of our office. You can see within it like a Franca, there's some UR5s, Trossens, ARCs, some mode manipulators. The number of things that we kind of are able to collect data over and learn from, I think is like really a result of this team. Cool, that's the end, and I will do questions. That's my email and our website, and we do internships and jobs and things like this.
All right, we have time for questions.
And I'm going to run over the mic to you.
Thank you for a great talk. So I have a question about the cross embodiment. So did you do any special handling of the different action space and observation space?
No,
and maybe
like nothing.
maybe like following up a question is that, for example, in a knowledge isolation framework, you can replace the fast tokens like hypothetically with the language tokens. So for example, just represent everything in language, like move right 3.5 centimeters, rotate yaw 30 degrees. So I think this is like a unified action space between different embodiments if you use end effector post control. So I don't know, like, what's your take on this? Like, do you think it was to improve the performance and keep the VRM even better?
Yeah, so I guess to the first part about cross embodiment, we don't do anything special. We don't like even, I mean, we like loosely align action spaces, but it's more like a, I'm not sure if it makes a huge impact. It's just something that like is easier programmatically to set up. I think it's an interesting area to study, like, can we get better transfer across them by doing that? Do different types of control modes, whether it's like end effector or joint, improve cross embodiment performance. We haven't necessarily seen like explicit signs in one way or the other, but I think it's an interesting area. And then in terms of the action representation, so I think something where you're like breaking it down to like move 0.5 left or 0.5 in this direction. First, I think it's hard to do that with high frequency control. Essentially, that grounds back to the like action representation that we had before, which is like these buckets of where to move, which is, I mean, if you were to think about it in say like joint space, this is maybe like move a centimeter to the left, move a centimeter up, and like to be able to do high frequency control, you really need to either have something that can represent much more fine-grained manipulation or like an action chunk. And if you were to replace it with something like move to the left or right, and you're starting to do tasks that are like, I don't know, flipping something over, it's a little bit harder to represent there. And I think that that language representation of actions needs to be as expressive as the final like action representation out of the action expert, or you won't probably get the transfer that you want. I feel like I gave a kind of long-winded answer, but I think it really needs to be as representative and as the final action representation.
Oh yeah, thanks for the great talk. I'm curious, so far you focus mostly on behavior cloning here, and I'm curious, what role do you think RL will play or should play in scaling up this robotics learning?
Yeah, I mean, I think this like task performance, speed, 100% success is like RL is going to be part of the solution. Whether it's like offline RL or online RL, I'm not sure. I think like online RL still has a ton of challenges for robotics around how do you explore meaningfully, how do you reset the scene and do it in a scalable way. But I think some way to elicit the best part of the performance is really important. As a company, this is an area that we're really focused on now. We feel like we kind of broke it down into, at first we're looking at, can we just like train a capable model that can do some complicated tasks? Then can we train a model that can do a task in a new scene in a generalizable way? But the last section that we feel like is still somewhat unsolved is this performance. And I think like RL is going to be like a key to this.
Hi, thanks for the talk. I was just wondering, when you referred to web data, is this more like, I mean, you had one slide that had some sparse details about it, but is this more like generic VLM pre-training data, or is this more like videos or like egocentric videos of just.
It's more like the generic stuff right now. So not much in terms of like egocentric video or anything like that. It's something like we've loosely thought about, but I think the quality of the data set still makes this relatively challenging to use. But it's more like VQA, V2, and COCO, and other data sets like that. It's like a planning problem.
I had a question on the data collection side of things. You said that that was an issue. Do you think, like, I guess, what's your guys' approach to kind of exponentially grow it to where GPT-2, GPT-3 is? Or do you think, like, this is a field where it's just always going to be data scarce? And then, like, that's like a model architecture problem.
I think once models are out in the real world doing real world things, we will hopefully no longer have deep data scarcity. So a lot of it is getting to a point where a model is capable enough to be doing something useful in the world. And now you have this like ability to train on that, and you essentially like build this flywheel of putting things out in the world. But I think we need to get to that point before we can get out of the scarcity.
Hi, thanks for the great talk. So I noticed with the types of data that you guys are using, you mentioned, I think, web data and also real-world data. But I was curious if you could talk about, I guess, like robot simulation data, and if that was something that you guys were considering, and I guess what were some of the trade-offs on using that versus not using that?
Yeah, so right now we're not considering it for training. We're looking a little bit of it for evaluation, where I think that's a place where we can get a lot of signal over controlled tasks. In terms of training, it's not clear to me that you can generate really diverse, complicated, dexterous tasks with this. So we take like t-shirt folding. I think you could simulate that one task, but it would take a lot of work to get to a point where it matches the real world and does well. And if we then expand it to like all clothes and all scenes and bedrooms, it essentially requires still a lot of human input to do well and to get to a level of performance that transfers. And so it's actually not that hard to just put something in the real world and do it. And I guess all this gets to, at the end of the day, what matters isn't necessarily pure scale, but it's how you scale, and the diversity and the complexity of the task is more important than just like the broad scale that sim will bring you.
Hi, I have two questions. So the first one, I guess, is when you talk about tactile data. So right now, a lot of the models are trained on just images. Do you guys have plans to like incorporate tactile data for training, and how do you think that will improve your models?
Yes, right now we don't have any plans to. I mean, I think the fact that we can do some of these tasks without it makes me feel like, at least for now, it's not the bottleneck. I think some of it is that we don't feel like the sensors are quite mature enough. I mean, it's still like very an ongoing research topic about how do you get these into models, how do you, in a very robust way, when we're collecting tens of thousands of hours of data, use these sensors. And I think while those are being solved, we're mostly using just cameras. I do think there's kind of a nice analogy to, we have these wrist cameras, and the number of pixels in that wrist camera is about the same as the number of touch receptors on my hand. And so it's giving me this like close-up view of some type of contact. Things are slightly deformable. The match probably like bends in a subtle way. So maybe we're able to learn these, and we're already incorporating tactile feedback in a way that we're just not doing it explicitly. I mean, you take like the Yumi setup that has these like deformable grippers, like there through vision, you are actually seeing deformation. I could see this kind of playing out.
Thank you. And then the second question was about the failure recovery stuff. I'm under the impression that the more failure recovery data you have, the better or more robust it is.
Yeah.
I guess, are there plans to kind of collect more of that data, or how do you think you can kind of, I don't know, maybe overrepresent that data so that you have better data recovery or failure recovery?
Yeah, I mean, I think there's things like Dagger that can potentially do this. Otherwise, I think it's kind of hard to do at scale, because essentially you would need to like look through the data, see it fails in this way, but now we have 1,000 tasks we're training on. So for every task, we need to go through this process, close the loop over that, collect a specific recovery behavior, potentially collect the behavior where it actually like got to the failure. And I think we're definitely like thinking about it, but we don't have like a great solution to be able to do this at massive scale. I think potentially we can learn like through RL and evaluations, ways in which failures were recovered from or from successful rollouts of the policy and then improve performance and remove these types of failures. To me, that's like the more likely avenue. But
okay, thank you for the great talk. So I think one question regarding like the data collections, I'm wondering if you guys have like sort of a criteria regarding like the quality of the data. Saying, let's say collecting data is way more beyond like the number of demonstrations, also about like the diversity or also the distribution of data. So do you have any thought about that?
I mean, I think other than like platitudes, I don't have like a great answer. Like we do want diverse data. We want data in a lot of environments. We want high quality data. It's all right now fairly kind of ad hoc. Like you have people go through and label the data as this was success and failure and this was this quality or had these conditions. But I don't have any like phenomenal like algorithmic answers or like ways to do this at massive scale other than just deploy robots in different places.
Thank you.
Last question in the interest of time.
I'm sort of wondering, and I'm guessing this hasn't been done yet, like most of the work is single agent. Has anyone tried either like splitting the information between bimanual manipulators and having them try to complete the same task, or conversely, like putting two different robots that are trained on some tasks, or train them together, like, and have them collaborate? And I guess follow up to that, like, in the future, I think the hope is we can have, like collaborative robots, like a human could actually, hand something to these robots and they'd be able to figure that out. Do you think the solution to that problem is also scaling up data and just like getting more information and running more experiments, or is there some other thing that might be missing?
Yeah, I guess to the last question, probably I think scale will get us like a lot of the way there. And then we haven't tried using like multiple robots though. I mean, each arm is its own robot, and we do collect single arm and bi-arm data. It also transfers across. We could definitely just like add 2 more arms to the mix, increase the size of the vector that's being output by the model, and then use that. And I think this would learn fairly well. I think so there are people who are like using this for a whole body humanoid control, and I don't know what the dimensionality of it is, but it's like 50 and above, which also could just be separate robots. And again, maybe you think of each joint or limb as a separate robot. In terms of like information sharing, it's not something that I've like really thought about. I think to start, I would probably just try the simple things of like train 2 separate models, but as long as they've been kind of working together during the data collection, potentially you get a lot of the information kind of out for free. So, thank you guys.